Hello and welcome back to another episode of the Oxford MAT Livestream. It's good to have you with us. Good to see you for some sequences and series. Hooray! It's the last one of these before our summer break, and we're covering the MAT syllabus piece by piece. And this is the last piece of the puzzle, I suppose, the last bit of MAT syllabus. The plan here has been that once you've revised the MAT syllabus, any past question should be fair game, that you could have a go at any past question. We're going to have a sort of summer break after this episode and come back and look at some past paper questions, which maybe gives you time to look at some past papers over the summer break and maybe just have a summer break. Right, hello to people in chat. I can see Len, A, Neutrino, Gatham, Keller, so Matthew, Maths2222 was in chat a moment ago, and Aya, and anonymous people, and more anonymous people, and more anonymous people if you want to join live chat. You can do so anonymously if you choose to do so over at slido.com/MATLIVE. We will do a how's your day going poll in a moment. I saw in chat people were learning sequences and series. Some people were telling me in chat that they learned sequences and series really recently in a book, or really recently in a classroom. Hello to the Riemann zeta function, great stuff. That's the kind of anonymous, like the default option is you can just be anonymous, but if you can also choose your favourite anonymous function. Right, anyway, the function that's mysterious that I don't know much about. There's some sort of extra mystery there. Sorry, I've been really taken by the idea of being the Riemann zeta function in chat. I'll find you one day. Right, okay. We're going to do some content on sequences and series. It's a normal live stream episode. Maybe you've seen one of these before. As always, you can get the worksheet in advance at the MAT Live webpage. And I'm saying in advance, even though I've started, because you could get ahead of me during this bit at the start, couldn't you? And you can also get the solutions. So if you feel that during the live stream we skipped a bit that you were interested in, then you might like the solutions on that live stream page. We're going to use some MAT questions here, and there are worked solutions for the MAT live stream resources. We've tried to put slightly more steps into the worked solutions just to give you a bit more guidance. Good. I'm a little bit under the weather. Sorry if my voice sounds a bit different from normal. It's not normally that great to listen to anyway. Slightly worse this time. We've done 3 summer schools back to back to back, and that is it's taking its toll. Let's do some more. Why are we not separating Chomsky and maths? Well, we've always had most of the questions in common for computer science and maths. What's the question in chat there? We've always had most of the questions in common. Recently, we changed so that it was even more in common, and this year we're just changing it so that it's entirely the same questions. There's a lot of maths in computer science, so same syllabus, same style of questioning. This year, exactly the same questions. Also keeps it simpler. I think if we'd always had the same questions for maths and computer science, I don't think anyone would bat an eyelid. No one would notice in a way. We've been moving in that direction for a little while. Anna says, hello, being my A-level teacher today. Oh, that's a reference to me, isn't it? That's me being your A-level teacher. I'm teaching Anna about sequences and series. I'm going to do my best impression. Good. Just doing it. Oh, it's a question about joint. Is JMC joint honours? Is possibly what they're thinking about. Versus straight maths or straight CS. No, I don't think it does at all. If you do maths and computer science at university, you're showing employers that you're interested in 2 things and that you've been studying 2 sorts of things. Maybe not in the full breadth or depth, perhaps, of people just doing straight maths or straight CS, but no, the career opportunities from maths and CS are very good. Right. Haven't seen JMC before for joint honours. Joint maths and computer science, but they say AJMC. It's a new acronym for me. Good. Right. What do I study? I'm a mathematician. Good. Right. I do maths. Lifelong learning. Does Imperial call it JMC? Is this a thing that we're learning? Joint maths and CS. There we go. So if you do a joint Maths and CS degree was the question, out of many JMCs. It's an imperial thing. Right, cool, I'm learning. Let's learn about how everyone's day's going. We sometimes see this poll in chat. Right, while they're voting on how their day was, that's going quite well in the immediate voting. Let's have a quick look at the math syllabus. These are the things that people learn in A-level maths or equivalent that we think people have seen by the time they do the math submissions test, which might not be yet. Math submissions test is at the time of live broadcast in a few months, so some people might not have learned this yet, in which case maybe you're going to learn it today, because I'm going to quickly revise the material on the screen, which is sequences defined iteratively and by formulae. We're going to learn in particular about two sorts of sequence, also known as progressions, arithmetic and geometric progressions. We're going to learn about sums of these things on the board to add together terms from one of these sequences. Adding together terms gives you a series, what you get when you add the terms together. And we'll learn something called a convergence condition. We're not going to learn anything about convergence in general or convergence of sequences. There's all sorts of fun stuff that people do at university on these topics, at Oxford at least. People learn quite a lot about sequences and series in their first year of university here on the maths courses, and I want to stress that you don't need to have already learned it before you do university maths at Oxford, and certainly not before you do the math. So sequences and series, I saw someone in chat saying they were really looking forward to it because there's loads of interesting stuff. In some sense, we only do very, very slightly interesting things. The tiniest amount of stuff, right? And that's what I've got. So I feel like I've had this chat with people in chat before, but there is lots more to say about these topics, which is not on the syllabus. And if it's not on the syllabus, then you don't necessarily need it. You don't need it to do the questions. Sometimes that's a powerful thing to know, that you can do the sequences questions we're going to see today without using any kind of like high-powered stuff. So this is me talking directly to people who already know perhaps more than me about sequences and series. Easy, Tiger, we're going to use the things on the board. And there's some people who are learning those things on the board for the first time today. Let's find out how chat's doing. Chat's having that's 4.2, that's pretty high average. There are 4% of people in chat, which by the numbers I think maybe one person in the vote. There is one person who's having a terrible day, joined a live stream and joined the Slido chat of that live stream and clicked 1 star. I just want them to know that I see them. We're going to do some maths. Let's see if that helps. If not, it's the only thing I've got, so do my best. Right, what's going on here? People are still talking about JMC. Someone's been reading about perfect numbers. Good stuff. Right, okay. I'm going to keep chat on my screen so I can see chat. I see you. But I'm going to switch it off from the broadcast so that I've got more whiteboard space, including all this real estate over here above my head, for continuing these infinite sequences if I want to. Right, good, okay. There's asterisks in the syllabus because some of these things are from full A-level maths. If you are learning A-level maths and further maths together, so you've already done some further maths as well as maths, then maybe it's the case that you haven't got to the kind of second half of A-level maths yet. That might be why you haven't learned about some of these things yet. I hope that you'll learn about them when you get back to school in September. And for some of you, this might be slightly accelerated learning. Good, right. Should we go? Should we learn some stuff? I thought Sophie's got to go at some point quite soon, so it's partly to teach Sophie about sequences. Possibly. Can't actually remember if. Anyway, never mind. Right, good. Okay, so one of the things in the syllabus there is sequences defined by a formula. You're good at these, you know lots of formulas. You can do basically anything you can think of. So I've got an example on the board of n squared minus n at the top there, but anything goes, right? If you have a rule for what to do when you see the whole number n, then that's a sequence. Provided it's defined for whole numbers. I guess I mean positive numbers in your sequence. So that's written A with a little subscript n. which I think you might have seen in various places. I might write this to talk about the sequence. I guess this is the terms of the sequence technically, but rather than a collection. But let's not get into that right now. This is sort of notation to say what the nth term of the sequence. So this is the nth term, where nth is a little bit of a strange word, isn't it? I guess I mean that maybe A1 is the first term, A2 is the second term. There's a slight problem that some people like to start from A0 and then go to A1 and then A2. I guess this is a bit like counting, starting with 0, whereas some people really like to start with 1. If you think about it like this in the first way, then I guess this isn't the first term, is it? A1 is the second term, and A2 is the third term. The first 3 terms are numbers 0, 1 and 2. That makes some people feel a bit unwell. So some people like to start from 1, so that you have the first term, the second term, the third term, and your first 3 terms go up to 3. But I think some people, especially people who like computer programming, really do like starting from 0. For math questions, it explained in the question exactly how the sequence works if you're given a sequence. So don't worry about this. I'm just letting you know that some people out there count from 0 and some people start from 1. Oh look, here they come in chat now. I knew I've said enough things about feeling slightly unwell that that's got chat engagement from all the people who want to start at 0. Yep. Okay. I see you, don't worry. Okay, I'm making the point that you can just have a formula for the terms. So this would be a formula like an equals sine n. That's a pretty cool one, because for any whole number n, you can just plug it into the sine function, see what happens. You know some of the values of this, I think. If I'm measuring n in degrees or something, then you know sine of 30, you know sine of 60. So 60th term of this sequence, sine of 60. Okay, that just gives us a value for each number n. That's your aim. People might have, if they've got multiple sequences, they might give them different names. The names might be different letters, so you might have a sequence bn, for example, if you have 2 in the same question, maybe an an and a bn. Also popular are capital letters. People especially like calling sequences things like fn, especially if they're thinking about the Fibonacci numbers, or capital C subscript n for their sequence, especially if they're thinking about the Catalan numbers. These are 2 famous sequences that I think we're going to meet in a minute. So Desmos, yeah, chat is now doing their chat engagement. Desmos starts counting from 1, MATLAB starts from 1, but most people seem to think that that's some sort of mistake or sin. When I was a student, I learned MATLAB, so I start from 1 most of the time. And Integration Bible in chat tells people that Matt Parker has some content about starting at 0 versus starting at 1. So I think I'll leave it to Matt Parker to regale you with more stories about starting from 0. For now, I've got in brackets there, the first term might be A0 if we feel like counting from 0, and I will leave it as a kind of subjective thoughts and feelings. Right, okay, that's annoyed everyone, hasn't it? Come down on one side or the other. There's this notation with a big sigma. Sigma's Greek letter, the first sound of the word sum. The letter S, which is sigma, whatever. This large sigma notation works like this. It's a little bit like, you know, in integration, you have limits of your integration over here, which some people write like this. And then you have a thing that you're supposed to be integrating. For integration, you also have this kind of decoration over here to tell you which variable to integrate with respect to, but some people do write it down here on the integral as well. That's the notation that some people use for integration. And there's a very similar notation for summation. The summation notation looks like this, big sigma. K equals, maybe so k might be like 0 down here up to n minus 1, but you could do whatever you like for these limits in general. Will stop you. They can depend on other letters, they could be numbers. It's normal to have something down here telling you which variable is changing. There's a viral tweet that I've seen that explains to computer scientists that this is a bit like a for loop. So it's a bit like for k is 0 to n minus 1, and it's inclusive. I don't think any computer code actually says inclusive in brackets. I think computers have different ways of doing stuff, but yeah, do this. Calculate and add. Computer code, what does that look like? So the summation stuff might look like this, to say take the terms of your sequence where the value of k should go from perhaps 0 up to n minus 1 and add them all together. So this thing that I've written out here means, so I take k from 0 up to n minus 1, and that goes like this, a0 dot 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 all the way up to n minus 1, and add them. So put plus signs in between all of these things. And it really is like a kind of list of things for some range with plus signs in between. That's what you're up to. Yeah, the truth was these scary math symbols are just for loops, and some people found it helpful, which was good. Not on the map, but there's a similar one. If you want multiplication instead, that's called a product. People use capital pi for the first sound of the word product is p. We use the Greek p letter, which is pi. And I just like seeing the capital pi symbol. It's like a very tall pie. It's just sort of nice, you know. It's like you finally meet pi's older brother. Just need to do a product. So list out the terms that you want and multiply them together. This notation does trip people up a little bit, so I'm going to just do a couple more examples to make sure that we're happy. Almost everything can change. It's quite flexible, except for the big sigma sign. So something like this of, I don't know, maybe I'll write out what my sequence is. So maybe I'll use like I squared minus I or something. That would mean plug in the numbers 3, 4, 5, stop when you get to 5, into this expression and add them all up. Which might be a sum that you can do, right? So you might be able to actually calculate this. So it's gone behind my head. You might be able to actually calculate this. 3, 4, 5 in they go, if you go and add. So even if the notation looks opaque and tricky, you might be actually able to do some stuff. Good stuff, right. Okay, I don't want people to be like put off by this notation. We've got a question coming up which counts 2 of these at the same time, including an infinity at the top. This one doesn't make any sense if you put infinity at the top, because you have to keep adding together enormous numbers. Maybe you could imagine that if the numbers were not getting so enormous, but if the numbers were all tiny, then maybe you could add together lots of them. More about that in a moment. Okay. Why have I got 2 versions of this? Oh yes, this is talking about the sum of the first, on the page at the top there, the notes at the top, it's talking about the sum of the first n terms, where you've got to be really careful if you're counting from 0, haven't you? Yeah. Oh, you could split the sigma up. Yeah, and it says, is it 38? And now I've got to think. 6 and 4, 12 and 20. Yeah, 38. Yeah, I agree. Cool. Which is good, because this looks maybe terrifying, whereas the number 38, nice and friendly. Good. Hugo says we can split the sum up, and I guess that is true. But you could rewrite this sigma as being like sum from 1 to 5 minus sign sum from 1 to 2, and oh my goodness, I've got so many potential out by 1 errors, right? So if you only believe in sums starting at if you only believe in sums starting at 1, then you can rewrite the sum from 3 to 5 as being sum from 1 to 5 minus the sum from 1 to 2, if you want to. You know, if you only believe in sums starting at 1. And this introduces a couple more terms that Anna would now have to add in and then also subtract it, and it's going to get to the number 38. Right, okay. In general then, these things are quite tricky to calculate because you've got to evaluate your function or whatever at the different points, different numbers, and do lots of adding. There's a couple of special cases where we can actually simplify the sum quite nicely. Oh, first, do I want to talk about relationships? Yeah, I think I do. So for the Fibonacci numbers, and I suppose in general, not just Fibonacci, but something you've maybe seen before is the idea that the nth term of a sequence might depend on previous terms. If you've seen any kind of proof by induction or something, you might have seen this kind of relationship between a number and a previous value. Fibonacci numbers use the previous two values. The Fibonacci numbers are ones that go 1, 1, and then add together the previous two numbers. 1 plus 1 is 2, welcome to the MAT Livestream. 1 plus 2 is 3, 5, 8, 13, 21, and keep adding. These are defined, so for the Fibonacci numbers, these are defined not really by a formula for the nth term, but by something kind of implicit, which says that there's some relationship. So for the Fibonacci numbers, they're defined by saying that f0 is 1, f1 is also 1, then for n greater than or equal to 2, fn is equal to the sum of the previous two. This is something to watch out for, where this doesn't give you a formula for the term fn. Well, I suppose. No, it doesn't give you a formula for the term fn, except in terms of other stuff that you would have to go and calculate. So instead of being defined by a formula, this one's defined iteratively, or if you prefer, in some sort of recursive way, where to know the value of this, you need to know the previous things. Yeah. Okay. You need to know the values of the previous terms. So I suppose in order to work out that 55 at the end, I had to know the previous two values, 34 and 21, and working backwards. So if I want to work out that 55, I've got to work backwards. If I want to know the 100th term, I've got to work backwards. That's a pretty common situation. Sometimes you can get around it by finding finding a formula for the nth term, but in general in life you shouldn't expect to have a tidy formula for the nth term. Formulas are nice when you can get them, but not always. There's not always a tidy answer. Which means sometimes we've got to deal with things like this, where we just know in terms of the previous values. Okay, I'm sort of hoping that people have met the Fibonacci numbers before in life. If not, they're kind of cool. They're worth a Google search. I'll try and spell Fibonacci to help you with your Google search. Other search engines are available, I suppose. I reckon it's like this. They're nice. You don't need to know anything about them for the math submissions test. Oh, slightly off the screen again. You don't need to know anything about them for the math submissions test, but just for your general education. Yeah, okay, so the conversation that's going on in chat is around this sum with the I squared to ask, somebody in chat knows a formula for adding these together, and that formula is not on the MAT syllabus. So it's great that they know it. I'm very proud of them. Well done. But you're not expected to know how to sum square numbers for the math submissions test. Numbers, yes. Square numbers, no. Let's do numbers. It is a standard result once you know it, but not everybody knows it. So, good. Okay. Also, even if you know some quick way of adding together square numbers, I think for this question on the board, it's easier to just add together some square numbers, isn't it? 3 squared plus 4 squared plus 5 squared. I reckon I can do that one. Ooh, that's rather nice, because of Pythagorean triples. Good, right, okay. Let's talk about arithmetic sequences then. Here are 2 bullet points about arithmetic sequences, which is all I'm going to tell you about arithmetic sequences. It's Probably more I could say, but here we are. So arithmetic sequence is one where you've got a common difference between your terms. You keep increasing by a fixed amount each time. You've maybe met these in the sense that someone's shown you a sequence like this, and you have to guess what the next term is, or something. I don't know. Maybe they tell you it's an arithmetic sequence, or maybe they say, what's going on here? And maybe you've learned this trick to look at the difference between terms. This is where I find out if I did it right. To look at the difference between terms, there we go. Which, if that's constant, that the difference is always the same. If the difference is constant, it's called an arithmetic sequence. Yeah, and there's conversation in chat about whether I was the right letter to use, which, fair enough. Yeah, probably shouldn't have used I. There's no complex numbers on the mat, so if you're worried that your question might involve complex numbers, great news. It doesn't involve complex numbers. This is making me smile because chat is usually very, very keen on making everything about complex numbers. I'm always very keen to make things not about complex numbers. Nothing against complex numbers, they just happen to not be on the mat syllabus. Right, okay, arithmetic sequences like this one. There is a formula for what happens when you add together the first n terms, which maybe makes sense, right? That you've got these terms each involve some amount of adding. So when you add them together, add them together, that's even more adding. It's pretty clear what happens to the a's, right? If you've got n terms of this sequence and you add them together, you should probably get n lots of a. The formula in the notes there doesn't make it immediately obvious that you get n lots of a, does it? N over 2 times 2a plus some more stuff, okay. So that's what's going on with those. But the terms involving this common difference d here, when you add those together, well, that's a sequence that goes 1 lot of d plus 2 lots of d plus 3 lots of d. Those are the triangle numbers. If you know about triangle numbers, that's what you get when you add together 1, 2, and 3, maybe 4 and 5 and 6. You keep going and adding together the counting numbers. You get a sequence called the triangle numbers. There's a formula for them. If you like, it's part of the thing on the board. So when I look at that formula with the a's and d's in, I kind of read it as having two separate parts. Something to do with a. If you make the first term larger, then well, sure, all the terms get larger, not in a very interesting way. All the terms just get larger by that much. If you make a larger, and then your sum will get larger if you add together the first n terms, because of course it will if you make each of those terms larger by some amount. And then a separate effect for what happens if you make this kind of rate of increase larger. If you make d larger, so instead of 4, if I use 5, then that will be 8. And then this one will be quite large. It will be 13, which is quite a bit bigger than 11. And the next one will be 18, which is quite a lot bigger than 15. So increasing d kind of has a different effect that has maybe more effect over adding together n terms, I don't know. Which is why there's a separate factor in there. Yeah, it's a lot easier if you think about it as n times a plus d times the, I think it's the n minus 1th triangle number. This is where maybe counting from 0 is a good idea, right? Because the general formula, I haven't written it on the board, but I suppose my general formula has to be something like an is equal to, and the people who count from 0 are going to say just a plus nd, right? But people who count from 1, if this is a1 for my sequence and this is a2, then I need to write a plus n minus 1d. So I think it's something like that. Formula on the board is something like n times a plus the n minus 1th triangular number. I think. Yeah. Triangle numbers normally go n plus 1 over 2. This one goes n minus 1 over 2. It's like the previous triangle number. To allow for the fact that if you have two terms, you don't get to see the plus 2d. You have to wait. Yep. All loads of out by 1 errors. Here we are. Here we are, out by 1. Cool. Okay. So different ways you can think about that. There's another mnemonic that people see. Okay. There's another mnemonic that people see, which is something like take the first term plus the last term out of the n that you're adding together, divide by 2 and multiply by the number of terms. The step of adding them and dividing by 2 is something like calculating the average term. There's a famous story about this that I guess I have to do, because if you learn this in school, they'll also do the story, which is that Gauss has to do a version of this sum. In the story, Gauss is a child. Gauss has to add together all of these numbers, add all of these numbers, and Gauss has the realization that if you pair them up like this, so 1 pairs with 100, 2 pairs with 99, 3 pairs with 98, and so on, then you get lots and lots of copies of 101. You get kind of that many copies. So dividing by 2, the kind of average value of everything is 50 and a half. You're slightly larger than 50 because, yes, you don't have 0 and you do have 100. So there's a slight bias to make these terms slightly larger than 50 on average if you pair them up. Yeah, 50 pairs with 51 in the middle. The average is kind of 50 and a half. So maybe this is for stats fans or something, but the average is 50 and a half. The total is 5,050. If you want to think about it like that, then the fact that there's a common difference just means that things got to balance out on both sides. I'm going up by common difference, going down by common difference, have the same effect on the total. Yeah, the number of pairs is half the terms. Depending on how you're thinking about it maybe matters whether there's an even number of terms or not, which is weird because in the formula up there, it doesn't matter if n is even or odd. It matters a little bit whether you're talking about the average of each of the terms, the average of pairs of terms, the average term in general. Matters a little bit how the pairing works if you think that there are even or odd numbers of terms. Sometimes you want to talk about n over 2, and sometimes you want to talk about n minus 1 over 2, I think. Anyway, never mind. I've gone weird. Let's get less weird. Anyway, the story is that Gauss did this question before the teacher had left the room. I don't know why the teacher was trying to leave the room in the story. Yeah, thought it would keep Gauss busy, and it didn't. Can't keep Gauss busy. Right, cool. Okay, different ways to think about the same formula, but point I suppose I'm trying to make is that I need you to know that formula for adding together numbers with a common difference. So that if we had to, you could add together all of these numbers by doing something like first plus last divided by 2, 13, multiplied by the number of terms is 6, so I think it's 78. I actually think that's more impressive if the numbers are all weird. 10, 21, 36, 55, 78, yeah, good, cool. Gauss thing checks out. Right, yes, Keller's trick in chat is to copy out the sequence backwards, and that feels more like it works. Let's do that on the board. I feel like that feels like it works, even if there's even or odd numbers of terms. These are all 26. And these are all 26, and then I guess divide by 2, multiply by 5 or 6 or something. I'm losing count. Right, good. Okay, I'm moving on before I say anything really stupid. Let's talk about geometric series instead. That's all I've got on arithmetic sequences, by the way. I've got geometric sequences and no other special sequences. So geometric sequences are a really similar idea, where instead of adding, you multiply. So multiplying gives you terms like this, where the general term is, let's be careful, if the first one doesn't have any r's in, and I'm calling that a1, then I suppose the nth term, in the sense that the first term is a1 over here, the nth term is something like a times r to the power of n minus 1. It's the nth term. It's had n minus 1 multiplications done to it. Sort of similar idea, isn't it? So let's have an example of this. something like 3, then double it, then double it, then double it. And these turn up in lots of places involving probabilities and processes that geometrically multiply things lots of times. Some geometry problems are just solved by spotting a geometric series, which is, I guess, how they got the name. Yeah. So occasionally, question in chat about leaving it in index form. Occasionally, multiple choice questions will have the options in this kind of index power of something. I can think of a question where the correct answer was something like 6 to the power of 2 to the power of 20, or something like that, where we really didn't need anybody to work out 6 to the power of 2 to the 20. There's multiple choice though, so that was just one of the options. Something like that. Okay, here's a geometric sequence. Less clear how we're going to add the terms together for this one. There is a formula again though. There's the formula on the board for adding together the first n terms. Again, being careful. This is the first 1 term. These are the first 2 terms. The first 3 terms include this one. The board has 4 terms on it. And there's a formula for this that comes with a kind of explainer, which I've put in the notes. I'm not going to copy it out here, but there's a reason for where this formula comes from. If you like, so not quite talking about the thing on the board, but if you like, then 1 minus r to the n, which is part of the formula, that's a polynomial that has a factor corresponding to the root at r equals 1. So if you remember way back the factor theorem, which I think was in the first episode of the MAT livestream this year, factor theorem says that 1 minus r to the n has a root at r equals 1, so it has a factor. And then the question is, what's the other term? That's a factor, like 1 minus r. That's what's going on here. The other term is basically the geometric sequence that you're, the geometric series that you're looking for. That's the sum of lots of terms. Yeah, good. Yeah, Gavin in chat is explaining to me how to multiply by r, subtract that from the original thing. Let's just notice that there are 2 ways to write this. Depending on the context, you might prefer to write this, or you might prefer to write this. So if you're seeing these, I put a minus sign on the top and bottom. If r is larger than 1 or less than 1, then it might make more sense. Like if r is the number 2, then it can feel a bit daft to write 1 minus 2 to the n and then over 1 minus 2, because it's negative. They're both valid, they're both equal, so whatever you like. I'm applying to, someone in chat's applying to Oxford CS after already completing an undergraduate degree in robotic engineering. Would I need to do anything differently in the MAT? No, you apply as normal, same application process. Integration Bible in chat asks about the remainder theorem, which is natural because I just mentioned the factor theorem. And the answer is, weirdly, no. The factor theorem is on MAT, but the remainder theorem is not. Which is weird because the remainder theorem is very similar to the factor theorem, but whatever. It used to be on the MAT, and then we realised that I think that A-levels changed. Anyway, we're not here to talk about remainder theorem. It's left over from the polynomial session appropriately. Okay, the thing that's different about geometric sequences is that sometimes it makes sense to ask what happens if you add together all of the terms. And that's because if we look back at the formula for adding together the terms of an arithmetic sequence, and we ask what happens if n is really large, well, it's just not a very interesting question. If you add together the first 1,000,000 terms, then, well, you know, there's that n over 2 at the front, that's huge. Inside the bracket, you've got 2 times a, which is probably non-zero, and then you've got n minus 1 times d, which is also huge if n is 1,000,000. Maybe positive or negative, I guess, but unless everything's 0, then the more terms you get, the sum just gets huge. Partly because of the n up front and partly because of the n inside the bracket. So it's not really an interesting question to ask what happens when you add together lots and lots of terms. of an arithmetic sequence, because as n gets very large, the sum just gets enormous. Yeah. Why don't we just give the factor theorem and the remainder theorem the same name, says Anna in chat. Yeah, okay. It's this other thing, but the remainder theorem is slightly better, which is why it's not on the map. I think it'd be nice if everybody learned the remainder theorem, but we've got other things to learn as well. For example, this. Here's a sum to infinity. Sum to infinity. Maybe you've seen integration to infinity, where the top limit is infinity. The idea is that you're going on all values of x out towards extremely large values of x. Keep going. For a geometric sequence, the notation looks like this, with an infinity symbol up the top. And here's the thing: if this common ratio r between the terms, if that's between -1 and 1, then when n gets really large, can't get really large between 1 and 1. If n gets really large, then this term r to the n, that's the only point where n appears in the equation. If n gets really large, then this r to the n will become very small. It's the only observation, that if n is absolutely enormous, then you sort of make this term really tiny. People say in the limit, if you take the sum to infinity, then it's like this term's not there, and you're just left with a times 1 divided by 1 minus r. This is an effect that you've seen before, I think. If you've seen something like 1 plus a half plus a quarter plus an eighth plus a 16th, this is the thing where you're sharing a cake with somebody, and you're both very polite. Nobody wants to take the last bit of cake. I guess you're sharing 2 cakes. You're sharing 2 cakes with somebody. Anyway, you take one of the cakes. Brilliant, that one. Slightly greedy, I guess, but let's think about that in a second. And then the other person, not wanting to be rude, doesn't want to take the last bit of cake, so they take half the remaining cake, and then you take half the remaining bit of cake, and then half the remaining bit of cake, and then you keep going, cutting off. And then you don't want to be greedy and take all of the remaining cake, so you just kind of half the remaining cake, and you keep doing this forever. Eventually we're dealing with tiny crumbs, and if you could keep doing this actually forever to have all of the terms of this sequence, then we'd get exactly 2, which is, I suppose, a theoretical statement about what this ... is doing. This kind of sum to infinity. This sum 2 to the minus n for n is 0 to infinity is 2. I suppose that's a theoretical claim about what's going on with that sum, but maybe that makes sense to you if you think about tiny crumbs. Yeah, there's an associated paradox to do with called Zeno's paradox, which suggests, can you imagine this happening in the real world? If somebody wants to get from A to B, they have to pass through infinitely many points. Is that even possible? Question for the philosophers. Yes, so then I was going to ask, I stopped myself, but in that scenario where you get every other term of the sequence, for you, I imagined you were sharing, so if you get every other term of the sequence, well, this is a geometric series as well, with first term 1 and with common ratio 1/4. So we can use the formula up there, because 1/4 is between -1 and 1. This is 1 over 1 minus 1/4, which is 3/4 down here, so 4/3. Okay, you get 4/3 of a cake, and the other person gets 2/3 of a cake. Oh, yeah, so you get twice as much. So this is not fair, just polite. Which feels like a clip, doesn't it? Okay. Right, feels like something you could cut out of context. It's not fair, just polite. Right, good, okay. So other versions of this, if you start with a different number, A might be different, and if you have a different common ratio, then R might be different. But if R is between -1 and 1, strictly between -1 and 1. then you can sum all of the terms. If you like, you're filling in the gaps just perfectly to meet up at the end. I have a picture for one of these, not with the 1+, but there's this picture you can draw with squares. I guess I'm still sharing out a cake again. So if you have a square, and then it's a little bit like a fractal, I guess. You cut it in 4. So you chop this up, and you take a quarter, and then friends take this bit each. This is a way of sharing a cake between 3 people. You get to the last corner and you think, oh dear, if you split that up again and keep going, then what you're doing is making a kind of smaller version of the original problem. There's a scale factor there, and if you remember I said that geometric sequences tend to turn up in geometric problems, there's a scale factor here which gives you what will happen as you keep going. But on the other hand, it's also sort of obvious what will happen if you keep going in terms of how much cake will you get total. You'll get a third of the cake, because as we keep going, all of the cake is getting shared out, and it's being shared fairly along the way. So the sum of all of these pink slices of cake is 1/3. And this is a visualization of all of the terms in that sum, except for the 1+ in front. This is a quarter of the cake. This is 1/16 of the cake, and 1/64. So I said you were sharing it between 2 people, but maybe it's more fair if you're doing it between 3 people. Sort of taking both the blue bits and the green bits, and that's a geometric sequence as well. Something in this, finding geometric sequences within geometric sequences. I'm having fun. Did I mention this at a Maths Open Day, or somebody mentioned this at a Maths Open Day? Slicing pizzas. Oh yes, David. David did this. Ah yeah. He actually did it to a pizza, a square pizza, and he had some photos of what happens. Good. Okay, and there is a number file video, says Moses. Again, all the recommendations. Let's put that on the screen as well, just quickly. There's a number file video about sharing your cake perfectly between 3 people. I can't remember if it involves infinitely much cutting. The algorithm that I've seen for sharing a cake between 3 people involves infinitely much messing around. Right, okay. That is the content. That's what we've got. Let's do some revision questions. So the way we've been running these is you can talk about your favourites, or the ones that you want to talk about, or the ones that you found hardest. What I can't do is talk about all of them, because there are 14 of them. Let's see if I can put most of them on the screen at once. Here are first 5. So we've got some questions at the top to try to get to grips with some sequences defined by formulas and iteratively. We've got one of each there at the top, and there's some stuff about geometric sequence. 5 tries to get you to solve for some sort of quadratic sequence. You don't have to know what a quadratic sequence is, I guess, but it's got n squared in it. What else are we going to call it? There's a request for question 3 about summing up lots of terms of a sequence. I think that might be a geometric sequence. We'll find out in a moment. 6 and 7, both questions about converging or diverging geometric sequences. First time of arithmetic progression, common difference 3. What's the 13th term? Yes, and then I've got a bunch of questions about just playing around with geometric and arithmetic sequences. In case if you've just learnt about these words, then here's some questions to practice those. 11, I try to add this extra text. So positive even integers. Some people are not sure whether 0 is positive or not, and some people are not sure whether 0 is even or not. So just to make it really clear, I put this starting at 2 in brackets. After I typed that, I realised that including 0 doesn't matter at all for the sum. Oh, I guess it matters for what the first 100 are. So you've got to be clear where you're starting. There's a request for the last question. The last question involves a more complicated kind of sum. It's a it's a recursion relation. It's a sequence defined iteratively, but it involves all of the previous values of C and a complicated sum. And it's those are the Catalan numbers. I was requested to talk about Catalan numbers, so I think I might do that. Okay, so requests in Slido chat. I'm going to start talking about question 3, and then I think I'm skipping to question 14, which would be fine with me, but if you don't want that, then if we go through these quickly, then we can spend more time on math questions. But I just want to be useful. Whatever you want me to work on. Right, good. Okay, here's 3 then. So the sequence is defined by A0 is 1, and then after that, divide by 3. It's usually a good idea to work out a couple of terms of the sequence, just to get a feel for what's going on. We'll see a question in about 20 minutes where that's the entire question, is to get a feel of what's going on from the first few terms of the sequence. Good. Yeah, going to talk about the Catalan numbers. Good. Okay, gonna get there. Here are some numbers. We're asked to find A0 plus A1 plus dot 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 plus A10. I'm being really careful. I suppose the general term here is something like this is 1 plus a third plus a ninth plus, oh, I've got to think. So A0 is 3 to the minus 0, A1 is 3 to the minus 1, A2 is 3 to the minus 2, 3 to the minus 3, okay, so it's going to be up to 3 to the minus 10. So what do I think is going on? I think this is a geometric sequence with first term 1, and I'm looking at the sum of the first 11 terms. So I'm supposed to write down something like A times 1 minus R to the power of n, which is 11 because I want 11 terms, divided by 1 minus R. And this 1 here is just because the first term is 1. I had to work out a few terms to spot the pattern and make sure I understood what was going on. I think it's this. And I think the sum of all of the terms does converge, because this is a geometric series. This is a geometric series with first term 1 and common ratio 1/3, which means the sum to infinity should be A over 1 minus R, which is, oh gosh, that's 2/3. This is 3 over 2. 1.5. Let's do a quick sense check. 1.5 is a bit larger than 1 1/3, but not very much larger than 1 1/3. Now there's some more tiny terms that will get added together. They're all tiny. Maybe this will be 1.5 overall. Okay, tricky thing there that the sum from A0 up to A10 is 11 terms. So if you've memorized a formula, you need to make sure you're putting in 11 for how many terms you're adding together. Okay. So this is a case where you can do sum together all of the terms. There's some further down I want to point at. For 6 and 7, the common ratio has been a little bit disguised here. 7 is perhaps tricky to spot that question 7 really is a geometric series, and that's because of the minus signs and the fact that it starts at 2. I suppose the question could make it clearer that the pattern keeps going. It's a bit mean not to tell you that it really is the geometric sequence you think it is. That each term you get multiplied by minus x over 2. The minus sign doesn't matter for the question of convergence, but the over 2 is perhaps clear from the pattern. Anyway, minus 2 does work. Yeah, I mean minus x over 2. I'm talking in bursts as I try to think about minus signs, because, oh gosh, I think it's been about 50 minutes and I haven't made any minus signs mistakes yet. I was not expecting anybody to simplify their answer here. And maybe I've annoyed you by moving on without simplifying 1 over 3 to the 11. I'm really sorry if anybody calculated 3 to the power of 11. Let's add a note to the question for next time so that nobody else in the future ever tries to simplify 3 to the 11. Oh, and the question also wants a to the 1000. It also wants a 1000, right? Okay, let's add a do not simplify tag to that question. Trying to get you to practice writing down the formula. Not can you work out 3 to the 11? Good. Okay. Maybe that's the person who was having a 1-star day. If you multiplying 3's together all day. Oops. Wait, question 3 is nice if you find the derivative. Can't do the derivative of a sequence, can you? What? Oh, I don't want to think about that. It means 7. Oh, well, never mind. Okay. I guess 6. Anyway, never mind. Because I've used the letter X, I think some people in chat are thinking about differentiation, calculus, and polynomials and things. It's not a polynomial because the powers keep going. Good. Okay, there was a request for question 14 as well. I threw 7 in just for because I wanted to talk about 7, but it should go back to being useful. Okay, let's talk about this sum. So I think the smallest values are actually the hardest ones to think about. In general, here's what's supposed to happen. Let's try and work out, I don't know, what do I want here? See n plus 1, so it's also weird that it's got an n plus 1 on the left. If n is 5 or something, then this is an expression for C6, says that you're supposed to add from like this. So when I is 0, you put I in both of these places, wherever it appears. And then when I is 1, you get this. Then when I is 2, and we're going to keep going. And we're going to keep going. And we're going to keep going. And I wish I'd picked 4 instead of 5. We're going to keep going until we get to I equals 5 at the top. And then we stop. Like we're a computer doing a for loop. We're going to calculate these things like that. And add them all up. That would be lots of work, which is why we're just working out the small values at the start. Here are the tricky ones then. So to find C1 in terms of C0, I think we need to start by summing from I equals 0 to 0, which is going to make everyone unhappy, isn't it? No, maybe it's fine. I shouldn't tell you that it's going to make you unhappy. I should just do it and see what happens. So this looks really weird. If I put n equals 0 in, then it does look really weird, especially with this negative I down here. But luckily this sum says put in I equals 0 and stop when you get to 0. Okay then, that's just C0 squared, which is the number 1. So we're okay. It's a little bit freaky, but we're good. Let's move on to n equals 1. So that's given me the value of C1. I'm well, happy as pushing it, but I'm still here. Okay, I'm not super happy with this 1 minus I. I guess this is designed so that I get very nervous if this looks like it might be a negative number, because I don't know C for negative numbers. But I think the limit's designed to be a kind of safety rail. So you can sort of see the pattern here is that the numbers on here are going up and the numbers here are going down. This is me describing to you what I and n minus I look like. So what is this? C0 and C1 are both 1, so this is and C1 and C0 are both 1, so this is 1 plus 1, and 1 plus 1 is 2. Welcome to the MAT Livestream. 1 plus 1 is 2. That number is 2. I will explain in a second what these are for, but I'm just going to do like this. So you're supposed to take the values you've got so far and also write them backwards like this, multiply the pairs and add them up. That's how you get the next one in the sequence. The reason that in maths, the reason you have this notation and stuff is that actually the thing I just said out loud is a bit mad and quite hard to do precisely. If you wanted to say precisely what you meant, then you would end up writing something like what's on the board. But it's useful sometimes to have this kind of idea in your head of what's going on in terms of like action words. I don't know, but things are going kind of forwards and backwards. I'm going to go for the next one just because, you know, CI in that expression, CI is kind of all the previous terms because I goes from 0 up to n. So that's what those are. And at the same time, see n minus I, that's zipping down the other way. So kind of 14, 5, 2, 1, 1. Which is, oh gosh, 28, 38, and 4 is 42, which is a nice number. What are these for? These are for lots of things. These are called the Catalan numbers. The Catalan numbers turn up in lots of different places. One of them is the number of mountain ranges you can draw using up strokes and down strokes like this. So mountain range is made of these or these, and it never goes below the horizon. Never going below the horizon. The number of ways you can do that, so using in this case 6 things like this, is one of the Catalan numbers. So small mountain ranges, you go up and come back down again. But for this many, I guess maybe it's 2n number of slices or something. There's kind of 2 of these, and then if you have slightly more, I guess, yeah, I'm missing a factor of 2 somewhere. They have a formula, like they are like the binomial numbers. There's a relationship to the binomial numbers. You don't need to know any of this. They're just cool numbers. They come up in lots of different problems. My kind of favourite place that they turn up is this, you know, this thing where you're trying to prove to somebody that the angles inside a pentagon add up to, well, whatever they add up to. In order to do that, you need to chop the pentagon up into triangles because you're trying to convince them the angles in a triangle are 180. There are 3 of them in here. I mean, in order to do that, you need to chop up your triangle chop up your pentagon into triangles. There are 5 ways to do that. 5 ways to do that because, well, you split it like this. You've got lines coming up from a point. For a hexagon, it's more interesting. Now, probably for a hexagon, you can do some sort of clever geometry to convince people that the angles are all 120 or something. But for a hexagon, there are lots of interesting ways to chop it into triangles. There are ways like this. There are ways where you do big triangle in the middle. We could do that one the other way round. Ways we use kind of zigzag, or maybe all of the lines coming up from the side. There are 14 ways in total. And it can feel pretty weird trying to list all of the 14 ways to chop up a hexagon into triangles using straight lines that don't cross each other and go from vertex to vertex. In general, it's Catalan number of ways. So for a heptagon with 7 sides, there are 42 ways to chop it up into triangles in order to prove that the angles add up to 5 times the angles in a triangle. Anyway, geometry, nice. Catalan numbers. I have forgot to bring it over. I have an entire book called Catalan Numbers, which has got about 200 different examples. In every case, the answer is Catalan numbers. But the challenge is to look at whatever the thing in the question is and try to work out why it's the Catalan numbers. So it's kind of like an exercise book where all of the answers are the same, but all of the questions are slightly different from each other. So there's lots of kind of like these paths and graphs. I don't know if you can see that on my camera. Okay. Good. Love the Catalan numbers. Just to be clear, facts about the Catalan numbers, not required for the math submissions test, but just this one time, I've gone off on a bit of a tangent. Somebody asked in chat, it's quite a good book. It is a little bit it's always the Catalan numbers. Okay, and there's other books are available. I'm not getting any commission from Richard Stanley, 4 copies of the Catalan numbers book before anybody asks. Right, good. Okay, that's probably quite enough Catalan for right now, though. Let us look at some math questions. Okay, it's 6 o'clock, so if you've been learning about sequences and series for an entire hour without looking away from the screen or blinking, then remember to look away from screens. I'm going to drink some water, you might want to do the same thing. Here's a question on the board. It's about a sequence. This is from 2016. It gives us something to do. It wants us to find the product of the terms though. So remember, math questions are unfamiliar. They don't just ask you things from the syllabus. They don't just ask you things from A-level classroom. Sometimes try to surprise you by asking for something slightly different. Integration Bible is aware of other uses of the word Catalan. Right. Okay. Getting my bearings. Yes, I sort of forgot that I was doing the MAT live stream for a bit. sort of did Oxford Online Maths Club for just a minute or two, and now I've got to just come back to math questions. Yeah, right, good. We've got a sequence. It starts with A1 equals 1. They tell us that's the first term. There are subsequent terms. Imagine if it was just A1 is 1, there are no subsequent terms. There you go, there's all the things. And we're asked to multiply these together. You might have noticed that it says see next page for hints. I'm not showing the hints on the screen during the live stream. If you want to see hints, you can get the worksheet yourself on the MAT live stream page. You can get, I'm telling you this because you can get previous worksheets if you've missed an episode or if you've joined in halfway through our broadcasts. You don't have to watch previous YouTube streams. You can just get the questions, hints and solutions from the worksheets, which are available as both PDF and web page on the MAT Live page. The web page one works a little bit better on mobile phones, so you don't have to zoom and scroll. It tries to resize stuff to the shape of your phone, which works quite well unless it's got a very long equation, in which case you might have to do some scrolling on your phone. It's quite an activity converting things backwards and forwards. Yeah, 2 sequences at once, right? Because it has this sequence of AN, which goes something like A1 is 1, A2 is L, A3 is L squared, ... Why am I writing them vertically? Vertically is the one direction I don't have any space. How many do we want? A15 will be L to the think hard 14, because each time you multiply by L, the first one wasn't L though, it was 1. So by L, maybe the worst choice. It's L to the 0 over here for A equals 0. Yeah, thank you, Cuba. And then we're asked to multiply these together. Product. Maybe you're expecting some, maybe you wanted some, because we have a formula for the sum, right? Formula is something like 1 times 1 minus L to the 15 divided by 1 minus L, but it's not that, we want the product. And then amazingly this turns into via the magic of powers, right? That this is L to the power of 1 plus 2 plus 3 plus ... plus 14. Gauss has joined the chat. This is a sum that you can do using arithmetic progressions. So this is a geometric progression, and up here, arithmetic progression, which is something like, depending on how triangle numbers work, right? 14 times 15 divided by 2, which is 7 15s is 105, I think. Is that one of the options? Yeah, it's the one that's just a big power of L's, not 14 of them. Cool, okay. L to the 105D, yeah, good. Thing to take away from this, or reflection point, sometimes the questions are going to ask you for things that you weren't quite expecting. Please read the questions carefully. Luckily this one, it could have been nasty, it could have had an incorrect option to do with the sum of the terms, but read the questions, I guess. Also, if this has made you notice that there might be some sort of link between geometric series and arithmetic sequences via powers, maybe you could think about trying to generalize this. Not with the L's, I don't like the letter L really, but maybe you could think about the product of terms of a geometric sequence. Product of terms of a geometric sequence, does this happen in general? What happens in general? Is there a formula for the product of the terms of a geometric sequence? That's something you might like to think about yourself. 2 questions in chat. One is asking about TMUA, which is another maths test. It's a maths test used by different universities, but also universities with strong maths candidates. They would like to give their candidates the chance to do some maths questions. It's multiple choice as well, so if you want more examples of multiple choice questions, you could have a look at the TMUA. It is slightly different from maths, but not very different from maths. If you need more questions, you could have a look. We've got quite a lot of math questions on the math page as well, but whatever. Similar level and flavour. And there's a gap year question. If you're doing a gap year, then tutors at Oxford at least will be interested to know what your plans are for the gap year in terms of keeping your math skills sharp, because we're not admitting people to start immediately, we're admitting for people to start in a year's time. For a lot of people, they're still in school, so it's clear what they're going to be doing for the next year. They're going to be finishing learning their A-levels or equivalent, and they're going to do some exams and then be ready for university. If you're on a gap year, it's less clear to tutors whether you'll still be as great at maths questions as you are now in a year's time. Usually people do have something planned. This is a reminder to tell us about that if you like. Otherwise, do the normal admissions process. If you're post-qualifications, then you might already have qualifications that you need, which would be fair enough. And then it'll be, yeah. If your offer says that you need particular grades and you've already got them, then you already got them. If we were already aware of them, then we might not ask for them. What am I saying? I said that in such a messed up way. I'm not going to try again. I'm just going to move on. They know what I mean. They've already got qualifications. Right, good. Okay, here's another one. It's a sequence. This one is defined recursively again using the previous 2 terms. So like Fibonacci numbers. Fibonacci says take the previous 2 terms and add them. This sequence, unknown origins. This sequence says take the previous 2 terms and do the ratio. You know, there's a formula in chat for the product of terms of a geometric sequence. I told you it was something you could think about. And then a different question: if you've already taken maths, can I fit this on screen at the same time? Yeah, just about. That last option on the screen is 3. Interesting. Chat's hiding number 3 while I quickly talk to chat. Here's a sequence question for everyone to think about though. If you've already done maths A-level, that's not that unusual. We think about 25% of people at different schools. I'm not really sure. We think lots of people do this. Maths department and the computer science department at Oxford have a written policy on our website somewhere that explicitly says that we would take maths A-level as part satisfying the standard conditional offer. So normally you'd be doing 2 more A-levels, further maths and something else. And we think that learning maths and further maths like that versus learning maths and further maths like that, series or parallel, we think you end up knowing the same maths and doing the same amount of work, so it's fine with us. For other universities and even for other subjects at Oxford, I have to ask you to check with the relevant department or college or university or whatever. But for maths and computer science at Oxford, we don't mind if you learn maths and further maths like this or this, as long as if you're doing maths and further maths, you're going to end up having done all the exams. Right. Okay. That was the question in chat. Is everybody sort of thinking about this? Is there a time limit on taking that? Yes, I'm afraid. We get all our applicants to do the MAT. So if you're the gap year person, if you did MAT last year, that doesn't carry forwards. That's because we treat people who are applying twice, so people who've applied again, we treat them as if they're a new applicant. We don't look back at previous applications, previous MAT scores, and you're in open competition with everyone who's applying in the new round, which means we would quite like you to do the same MAT submission test at the same time as them. But there's no limit, so you're not, it is fine in the sense that you're allowed to do it again. I guess bad news may be that you need to do it again, or maybe good news that you need to do it again. I don't know, and I'm not going to try and find out. Right, good, okay. AS in year 11. What to do year 11? No, schools won't let you. Oh, sorry, Sophie. 12. That's slightly different, isn't it? Because then that's learning A-level maths like that. I don't worry about it too much. There's this thing with maths students where some maths students are a little bit ahead and then have a slightly different A-level experience, and you have to trust a bit that people aren't going to get ahead with maths, do no other work, forget how to do any work. You have to trust that people are not going to do that. Maths at Oxford would be alright. People doing first exam in year 12 and then the further maths exam in year 13, but sorry, Sophie. Good, right, let's work out the first few terms of this sequence. The advantage of doing that for this sequence is that the question is then over once we've done this. So this exercise is a little bit boring till you work out the ratio of terms like this, but the advantage is that once we've done it, I promise you, it's over. So let's keep going. Because what I'm getting here is 2, 6, 3, 1/2. I'm seeing some of the numbers in the question. It's not the case that what I thought might happen is that the terms get very, very small, so the answer is kind of roughly 0, or maybe the terms blow up to infinity, so it's the biggest term or something. You could maybe prove that all of the terms are bigger than 3 after a while, but it feels like going up and down. So my best hope is that it's just one of the options for some reason. 1/6, which is quite nice. And then this is 1/6 divided by 1/2, which is, it's nice that I can simplify a lot of these. 2/6, which is 1/3, and then A7 is 1/3 divided by 1/6, which is 2, and then A8 is 2 divided by 1/3, which is 6, and then A9 is 6 divided by 2, which is then, at this point I say, hang on a minute, I've been here before. This thing that I'm doing now is exactly the same as this thing that I did before. These are the same. And once we've hit this bit that's the same, we get stuck in a loop. Repeating. Yeah. That's the thing that can happen for your sequence. Your sequence might be periodic. Might come back round again. Okay. I almost said like sine n, but then I realised, oh no, if n is in degrees, then like sine n, where if you had 360, you get back to where you were. Big smile for using degrees rather than radians. Right, okay, so this is going to be 3 again. And in fact, what's the pattern here? Every 6th term, it's going to be 3, so sort of like 6 terms later, you get another 3. And then another 1/2. So I just need to work out which of these it is. 2017. The question is from 2017. So every 6. Oh gosh. So multiples of 6 don't affect things. So remove all the multiples of 6. What's the remainder when you divide 2017 by 6? 2016 is a multiple of 3, and it's even. So 1 more than multiple of 6. So I think maybe 2. I didn't enjoy thinking about that. 2017. What a large number. But every 6 it comes back around again, so I can subtract some 6s. And I sort of have to do 6s go to 2017. There's some sort of freaky division kind of sort of thing. 371, remainder 1 or something. you know, I haven't had to do that kind of calculation for a very long time, but maybe you're better at that sort of thing than me. Okay. Bit of a grid, yes. 2016 is divisible by 6, thank you, chat. If you get access arrangements in the MAT, do you apply separately? Because for the Tamua, you had to apply for access arrangements earlier than when you can book it. No, for the MAT, you do it at the same time as registering. And the MAT is going to be the same time. So when registration's open for the MAT, which at the time of recording is in about 3 weeks' time, A-level results day is the, let me count, it's the 15th of August that registration's open for the MAT, and that's also going to be when you tell us about access arrangements. Ooh, chat's telling me about other exams. Let's have a quick look. Taking additional maths. A freestanding maths qualification. Is that good? It's not used in our standard conditional offers, so it's not something we would normally ask for a particular grade in. It's a bit like an A-level, isn't it? So also a bit like a GCSE. I did one of these. Did it benefit me? Yeah, I thought about some extra maths. That was good. I think I had to write a kind of mini investigation about whole numbers doing something in some sort of sequence, maybe a quadratic sequence. It was good fun. This is a small part of your application, because a large part of your application is what you're doing now to get ready for university, and how good you are at solving problems and doing your A-level stuff. Is it 336 remainder 1? Wow, I got that really wrong. Really wrong. Can I claim that I did it wrong on purpose to yeah, I started dividing by 7. It's pretty bad times. Not looking good for me in the Division Olympics. Right, good. Did you not hear? Paris, they're doing Division Olympics. It's gonna be great. Every country has sent their top division person to see some really large numbers. I'm sure that is a real competition. I shouldn't make fun of them, but just because I got one wrong, I shouldn't be mocking people who are good at doing division. Right, okay. Oh, AEA. Yeah, AEA, I've heard of AEA. That's another maths test. People are asking me about maths tests. In general, anything that's got tricky math questions, anything that's got tricky maths questions on, questions you can't do straight away, be it AEA, FMSQ, something, other acronyms are available. Anything you're doing that's tricky, it's probably good practice for solving math questions fine. Probably good practice for being a maths student, where you're going to be given tricky maths problems. And I sort of think it's good practice for real life as well, to be good at solving problems. And I don't just mean in a very narrow, if it's on the maths syllabus, I'm fine. It's good to have like some other kind of skills, that solving other stuff. Why does Oxford only have short information on the spec? Because there's a list of A-level topics, and I think everyone's learning them in A-level. We expand on it in this. Possibly missing a term. Yes, the first few terms of the sequence are where you should look for if you're missing a term in this sequence. Right, here's the one from the thumbnail. Let's do the thumbnail question. This sequence is defined as the sum of, and in words, that's the sum of all of the previous terms, because like it's not doing anything to the terms. It's just taking xk, where k is 0, 1, 2, 3, 4, 5, all the way up to n minus 1. That's all of the previous terms. I'm saying previous because it doesn't include xn, the current term. If you're working out xn on the left there, you need all the values of xk, where k is anything less than n, including 0, larger than minus 1. Right, what am I talking about? So sum of all of the previous terms. So we can work some of these out, right? Sum of all of the previous terms. All of the previous terms is just 1. So in the notation from today, sum from k equals 0 to 0 of xk. This is a sum where you start at 0, you keep going until we get to 0. Well, that's just a 0 then. So because x0 is just x0. whole. Just x0, which was the number 1. Or in words, if you want to add all the terms together and there's only one term, you should add that term to it. No, you should just have it on its own. Next term in this sequence is 1 plus 1 is 2. Welcome to the Oxford MAT Livestream. I bet you're glad you tuned in to learn about 1 plus 1 today, and then adding together all the previous terms, you get this. And then something starts to happen, which you may be spotted, which means that this sum with 1 over xk, this next bit we are doing something to the xk, putting 1 over each of them, and adding those up, is pretty good. Yeah, that is 3 times in one episode that we've added together 1 and 1 and got 2. It's one of the things we do the most successfully. Good. Oh, that suggestion from Maths 2 is a clever way to rearrange. Multiply it by 2 and sub it into itself. That does sound clever. Yeah, it sounds like a proof that this is happening. For a multiple choice question, I think I'm happy to just notice that it's happening. I'll leave it as homework, I think, to think about why is this happening? Why is it doing this? I guess if you've seen the sum of the terms of a geometric sequence, and you're happy with adding 1 to something, then once it's got into this pattern, I think it's going to keep happening. If you've seen binary and you've heard of bit overflow, then you've seen something like this as well. I think all of the placeholder values plus another 1. Oh no! Overflow to the next power of 2. Okay. What do we actually want to do? We want to add together the reciprocals of all of these numbers. Reciprocal being a fancy word I've just said out loud, which I sort of regret saying because all I really mean is 1 over each of these numbers. Here's the one you're missing. I think that's a cool shot. That's a cool shot at exactly one person. I think it's what's happened. So what is this? It's not a geometric sequence. Ah, rubbish. Because it doesn't have a common ratio, look. The ratio is 1, and then the ratio is a half, a half, a half, a half, a half, a half, forever. So I'm being silly, right? This is not a geometric sequence, but it almost is. Other than the first term, which is 1. Then it's a geometric sequence forever. So this is pretty good. Oh yes, I've missed a question. Thank you, chat moderator, for flagging the question that I missed. I will do it in a second once I've added this geometric sequence together, which is 1 plus all of these terms onwards, 2. So once you've spotted this kind of geometric nature, that there's a geometric sequence, not including the first term, but there's a geometric sequence going on in here. So it's kind of cool. There's a little offset geometric sequence. The first term is not the first term of the geometric bit. I don't know. It's got a 1 comma on the front. How many ways can I rephrase that? Yep, A, then all of the previous times. You get 2A, 4A. Oh, yeah, in general. Yeah. There's 1 plus geometric sequence. Yeah, good. And that geometric sequence, 1 plus a half plus a quarter plus an eighth. I've seen that one before. That gives me number 2. Good. So we get 1 plus 2 is 3. Is that one of the options? Yes, it is. Option D. Okay. The chat has noticed. Let's put chat on the screen. Chat has noticed that the answers are D each time, which forms a sequence with first term D, common ratio 1. That's a geometric sequence of the options. The question in chat is, why are the joint honours programmes not offered at all colleges? In some cases, it's because that college doesn't offer computer science, because they don't have a computer science tutor. And if they don't have a computer science tutor, they might not feel that they can have students doing maths and computer science, going to computer science lectures. What you've actually said is that 1/3 of the colleges have very few places for it, and that's normal, I'm afraid, because maths and computer science is actually quite a small course. So if you ask a college how many places they have, they will say very few. In recent years, more and more students being admitted for maths and computer science over the kind of trend in very recent years. There are more students being admitted for maths and computer science, but it's still a smaller course than maths by a long way, which means that if you look at any particular college, 0 or 1 perhaps. Some colleges maybe always 1 or 2, but it's not a huge course. And some colleges can't offer it at all. Okay. Oh yeah, it was also an arithmetic sequence with first term D and common difference 0. Ooh. Is there a website to check what colleges have what capacity? Not really, because capacity is a little bit flexible. I put some estimates for the maths degree, where the numbers are a bit larger. I put some approximations on the maths website. If you look at which college on the maths Oxford website, there's some approximate sizes, but it fluctuates a little bit. The college has got a spare bedroom and they want to admit an extra person, then I'm not going to stop them. So we'd certainly like that. Good. People in chat are not happy with this joke about the geometric sequence, so I'm going to go off the screen. Right, what is this? Yeah, maths 2 says, sorry, colon, and I don't know why, because the next thing they say is some maths, which I'm always keen for. It's this idea about adding together all the previous terms includes, when you're adding together all the previous terms, that includes, as a kind of strict subset, do we start at 0 or 1 in this question? 0. That includes as a strict subset adding together all of the terms up to n-2, which is xn-1 as well, which is why it's 2 times the previous term. Cool, nice. Well done for fitting that in a chat message. Good. Right. Okay, we've got half an hour, and we've got a couple of things we could talk about. Not the hints though. We've done these questions now. We could talk about this kind of classic sequences question from 2008. It's very good. It has several steps involving these two sequences, xn and yn, which work together. Each term is defined in terms of the previous value of each sequence. So to work out xn+1, you need to know the previous value of x and also the corresponding value of y of both sequences. But if you calculate both sequences in parallel, working through larger and larger values of n, then as a reward, you get an amazing approximation of root 2. So it's really good fun. It is. Right, hang on. Well, there are loads of questions in chat because I had chat on screen, perhaps, because we were in between questions, perhaps. Let's do some of those. So maybe we'll talk about this MAT question in a second. Let's do some of these. Recommend places to get questions that are like maths and Timur type questions. Not really. I mean, I also like step questions, AEA questions. I quite like the Enrich website, but it sort of doesn't matter where you find the questions. If you've done some UKMT stuff, some math challenges, maybe where you are, there's just somebody who hands out tricky maths questions on the street corner. Seems sketchy. Question their motives perhaps, but if the questions are tricky and you can't do them straight away, then it's probably still good practice. I've made that sound really weird. I'm quite tired. Right. Is it compulsory to choose a college to apply to? Is the question that made me do questions from chat. Because if you don't want to choose a college, you can make something called an open application. If you make an open application, then a computer algorithm will assign you a college, and then you'll be treated as if you applied to that college. So if you genuinely don't care, then some random number generators on a computer will care for you and will choose you a college. They won't take your preferences into consideration. They will take the whims of the algorithm into consideration and give you a randomly selected college. Not necessarily uniformly randomly selected, but if that's the sort of thing that you have questions about, then I think you might be caring about which college to apply to, and then you can just choose a college. Okay. Right. And yes, and then the next question in chat is to find a general solution to the equation in I, which is rather the point of the question, I'm afraid. Point of the question is to find several solutions to that equation. In fact, I think you end up finding all of them, but not knowing that you found all of them. I think that's true. Yeah, I think you find all of them in the process of this question, but not know why. So, question in chat, find all the solutions to this equation. Question for us, let's try and do that. So the point of the first part is just to find, well, whatever you like that works. What do I think? So check some small square numbers until you find some values that work. The point of the second part is to do some algebra. You've got these relationships for x n plus 1 and y n plus 1. And if you choose the numbers a and b just right, then it might be the case that the square of the x term minus twice the square of the y term is the same as it was instead of n plus 1 at the nth term. So again, reading it out in words gives you this way to say, on the left of that expression at the bottom of the screen there, on the left, that expression at the bottom of the screen, where I've got n plus 1s, that's like the n plus 1 version of x squared minus 2y squared. And on the right is the nth version of x squared minus 2y squared. The thing you're supposed to realise when you do that, so there's lots of algebra to take the expressions for x n plus 1 and y n plus 1 and so mess around with them so that this equation at the bottom there, this equality, is true. It's lots of work to do that, but the thing you're supposed to realise is that, this means that when you change n, the value of x to something squared minus 2 times y to something squared stays the same. So if I take my original values, which up here were called x1 and y1, the kind of starting point of this sequence, and you got to choose what the starting point of the sequence would be. For me, it's 3 squared minus 2 times 2 squared. So for me, the sequences start with 3 and 2, but for you it might be different numbers, different solutions. I suppose if you start with some enormous solution, you're not going to find all of them, but never mind. Let's not think about that right now. You don't have. I'm still thinking about finding all of the solutions, which is not part of the question. Never mind. Okay, so then you've got your values of a and b, which you're going to do some algebra, so that hopefully it will be the case that x2 squared minus 2 times y2 squared is also equal to 1. Where by also I mean like it's equal to x1 squared minus 2y1 squared, so therefore it's also 1. And then with 3's in, x3 squared minus 2y3 squared will also be 1. And that's kind of exciting because the numbers x2 and y2 could be much larger. So you could find, as the point of this question, is to find enormous numbers, capital X and capital Y, so large that they need capital letters, such that the equation still holds. Big X squared minus 2 times big Y squared is still 1, but the numbers are larger than 50. And I think you can find examples like 99 and 70 that work. Where I haven't found that by guessing, I found that by using the sequences in the question. So, calculating further terms of the sequences. The approximation xn over yn is supposed to get you thinking about how, well, these things still have x squared minus 2y squared is 1, so maybe dividing by y squared gives you perhaps ideas about what the ratio is doing. You want to get from the kind of only thing that you know about xn and yn, I guess you know a couple, but one of the only things you know about xn and yn is that xn squared minus 2yn squared is 1. Once you've got this far with the question, you know that in general xn squared minus 2yn squared will still be also 1, which means that you can probably turn that fact into a fact about the ratio, especially if yn is a very large number, so this 1 doesn't matter. Probably xn squared is roughly equal to 2yn squared if these things are both huge numbers. Like these two huge numbers are very similar to each other. They're like this, 2 times 4,900 or something. So probably this ratio is like 2, and that's the square. So probably the ratio of the numbers is like root 2 or something. Okay, those will be ideas of the question. The algebra itself is not very fun to do on the board. I think I'll let you try and do that to solve for numbers a and b. I think you probably end up with some simultaneous equations in there to try and make that equality true. And then try and choose values of a and b that work. They tell you to use positive values of a and b, which is kind of interesting. It suggests maybe you could do other values of a and b. I think would still be alright. I guess there's negative solutions to the original equation. How much do I care about those? Not very much. Okay. Yep, I think for this question, because I think what I'm going to do is move on and look at the other question instead. But I just want to pull out this bit of this really classic question. It is a good one. Which is this idea that the hard bit in 2 is doing the algebra, and probably once you've done the algebra, you want to move on and look at the next part of the question, which gives you this very mysterious instruction, right? Do the same thing as part 1, but better. Find a solution with enormous numbers, and that can be quite jarring to go from doing the algebra to now you're going to need an idea. It never says you need to have an idea now, but you do need to have an idea in part 3. And maybe that's related to the previous part. So maybe a good skill to have here is to reflect on what you've just done, that there's a reason why you're doing the calculation in 2. There's a reason why we might want exactly that equality to hold, with -2 on both sides. And if you can spot that says that equality says something about as n changes, the value of x squared minus 2y squared stays the same. If you can spot that, then you've already had the idea for part 3. You can see what they're trying to do here. That skill's really hard to learn. It only comes from looking at tricky problems where there is something going on for you to spot that something's going on. Most of the questions you see in A-level or equivalent, there's probably not anything kind of going on. I mean, there's whatever you're learning about is definitely in the question, but maybe nothing else. So wherever you can find questions where maybe there's something going on, step questions really good at this. I don't know that much about AEA, but after many pages of algebra, our correspondent has got back from the jungle of algebra to tell us that they've chosen A as 2 and B as 3. They've had, I guess, multiple simultaneous equations to hack their way through. Good practice. And I wants to know how that works. So, and I've just made Riemann zeta function do it, so I suppose I should have a go at it as well, shouldn't I? Let's do that. And then we'll move on and look at the other question. So we want the following to be true, where I'm copying out the thing that I want, and I'm already replacing the things with n+1 with the n versions using the relationships at the top. I'm just super keen to use the facts that I know in the thing that I want to show. So I want this to be true. I've got a definition or an explanation for what xn+1 is supposed to be, and also yn+1 involves these a's and b's, and I would just really like to get an equation out of this. So what is this going to be? If I expand these out, because I want to kind of compare these things, and at the moment this is all xn squared and yn squared, nice and simple on this side, and this is a bit of a mess. So maybe I would get something like this many xn squareds, and now I really need to concentrate. 24 xn's minus, that 2 is going to get me 4ab xn yn plus, what is this, 16 minus 2b squared yn squared on the left, which looks like a mess. So I guess this doesn't look anything like the right hand side, unless we have something like, for particular values of xn squared it might work out, but in general I think I want something like this. I don't want any xn, yn's. And if it only has to do it for particular values of xn and yn, then maybe you could get lucky. For example, if xn was always 0, or yn was always 0, or some sort of combination, then you would never need to worry about this bracket here. But I don't think that happens in general. I think my xn and yn are going to be enormous positive integers. Yeah, some combinations are a bit tricky. Okay, the surprising thing is that you can do this. This says a squared is 4, so let's take a equals 2 or something because it says positive numbers. This one makes me feel like I want b to be 3, and then wow, that actually works inside this third equation. I've got 3 equations. It's quite optimistic to try and solve this at all. It's maybe a clue that there's something going on here. You can solve these 3 simultaneous equations that are kind of pulled out of the coefficients. You can solve all of them just by setting a as 2 and b as 3. Question in chat. Yep, can't believe it's only positive values. The negative values would be fine. They give you negative values of yn plus 1, which is actually fine. It just means that your values of y oscillate sign. They go positive, negative, but take kind of the same magnitude values as everyone else's. The question tries to stop you doing that, just because you don't want to have those minus signs around. You would prefer, I think, to generate positive solutions to these equations. But the equations themselves, x squared minus 2y squared, if you put a minus sign on y, you're going to get the same thing. If you put a minus sign on x, you would get the same thing, but they've already told you to use 3 and 4 rather than negative 3 and negative 4. Question in chat, how do I know where I'll be taking the test? So you're going to register to take the test in a test centre. You need to register yourself. Registration is going to open 15th of August 2024. So you're going to register to take the test in a test centre, and then you'll take it at the test centre where you register. And we're using Pearson VUE test centres. So there'll be a lookup tool when you register so that you can choose a test centre to take the maths. Good. Okay. Some more stuff in here. What are we doing? Right numbers depending on how we feel. Yeah, I know. It's not obvious that there isn't another choice, right? That works for. Do we actually need these coefficients to work? It's not fully rigorous, right? This works well. I suppose this works if a is 2 and b is 3, then everything works. Is there another choice that works? I don't know. Easier to find an equation. Oh, different thing. Easier to find an equation with ax1 plus bx1 equals y2 by finding a y2 and y3. Starting with 3 and 2. I don't know how to find y2 and y3 unless I know a and b. Oh, I see, in terms of a and b. So I see the suggestion in chat is that you take, that's what you're saying about 3 and 2. You take your numbers that you had up here, and then you just go and calculate x2 is 3 times 3 plus 2 times 4 times 2 using the formula. Sorry, there's a 4 in the formula up there. And you calculate y2 using a times 3 plus b times 2, and then you just sort of check whether or not that's worked. Which means you're doing exactly all of this calculation, except it's everywhere I've got xn squared, you've got 9, and everywhere I've got yn squared, you've got 4. That's something like 6, and then you're going to hope that the whole thing cancels out at the end. Yep, fair enough. Less general, so less cool. That's a quote from chat. Pi isn't 3. Right. Okay, we've only got 10 minutes. So we're going to look at the cool bits of this last question. Here is one more question. It's about adding together these numbers where the thing is called a sum because it's got plus signs in it, because it says sum and its name is s. S subscript n is the sum of n things. And it is worth taking a moment to understand what those n things are. They've given us an expression there for the last one, which is n2 to the n. And I guess the first one is 1 times 2 to the 1. There's some stuff in between as well, but it's worth thinking about that. The question is just to match this up with a function of a particular form. The style of question here is the question writer knows a general expression for that sum. Maybe you do, maybe you don't, probably don't. It's a weird sum. Here's a formula, but they've replaced some of the numbers in the formula with letters A, B, and C. You have to work out A, B, and C from what you can infer about the sum. You're allowed to calculate stuff from the sum. They tell you to look at the first 3 values. It's a sensible thing to do. Yeah, sorry, there's an anonymous question about solving graph questions quickly. I don't know what a graph question is. I'm sorry. I think maybe you mean sketching graphs quickly, in which case the way I got faster was I stopped calculating values and I started thinking about behavior. So I thought about what was going on for large x or very small x to see if I could simplify the expression in those cases. So some complicated polynomial. I know that the highest power of x is the one that matters most when x is large, and the lowest power of x is the one that matters most when x is small. So maybe that gives you a way to think about polynomials. You might want to think about where it crosses the axis. That might involve plugging in 0. Might want to think about any asymptotes that it blows up, but I wouldn't go around calculating its values at 1 and 2 and 3 and 4. I know that is what I do for sequences. I can calculate sequences for 1 and 2 and 3, but I have sort of stopped plugging in values in the function. Okay, so I see the anonymous person has asked, while I'm talking, has asked, how can I improve solving graph questions quickly? So I see they may have been asking this for a while, and I still don't know what a graph question is, what it means to solve it quickly. I'm really sorry. I can think of loads of questions involving graphs. Let's imagine it's sketching. Graph sketching. Stop calculating values. Yeah, okay, sketching graphs, they say. Yeah. Stop calculating values, think about behaviors. Does it blow up at some point? Is it really large when x is big? If you make x negative, does everything go wrong? Does it do the same thing when x is negative, or does it do a kind of reflection when x is negative? Does it just become very, very small numbers when x is negative, like the exponential graph does? But I would do that. Instead of trying to plot the magnitude of values, to think about behaviors instead. Cool. Right, actually, I enjoyed talking about that more than I did about thinking about sums of numbers. Okay. Anyway, by setting n is 1, 2, and 3 in this equation up there, I guess it's an equation once you've equated something. The tricky thing is to actually work out what S1, S2, and S3 are. The tempting thing to say is that they are 2, 8, and 24, but sadly this is not true. Sadly that's not true because S involves some summing, it involves some adding. Sn is supposed to be the sum of, well, if you think about it, it keeps going up to n2 to the n, but it includes lots of stuff to add together. S2 is supposed to be 2 plus 8, and S3 is supposed to be 2 plus 8 plus 24. This is the most common problem I've seen with people trying this question, is to somehow notice that Sn always starts with 2 plus, and then the end point changes, but it always starts with 2 plus. So the values are these things, which is f of 1, f of 2. If these things are going to be equal, they should be f1, f2, and f3. Like this. So I guess it's like potentially equal to f1, f2, f3. Should try and, this has got consequences for the values of a and b and c. Maybe you can see that that's some notation. Yeah, summing. And change the do a substitution in the limits of your summations as maths 2 to do in chat. Okay. There's a show that part in there, which I'm not super excited about. I like the bit where it gets to, you may now assume that Fn is equal to Sn. So at this stage, I would just like to talk about these last parts of the question where we've got a formula. So at this stage, we now have a formula for, what is this? 2 plus 8 plus 24 plus ... plus n2 to the n. It's called Sn. We've now assumed that's the same thing as Fn, where we have some function for the explicit function f of n, which is quite nice. The question gives us two more sums, Tn in Un, and the challenge is to work out what these have got to do with the sum up here. The trick is to look at the sum Tn and try to look for 2, 8, 24, n2 to the n, which is easier said than done. But if you can find a 24, then you're probably along the right lines. So if you can look at Tn and find a 24, then things are going quite well. For Un, the tempting thing for me is to sort of do the question again, but with 1/2 instead of 2. So Un looks very similar, right? It's got the numbers 1, 2, 3 up to n, and it's got 1/2 to the n instead of 2 to the n. You can do a little bit better than that. Un has got a more slick relationship to the other things in the question, but the first thing that I thought of when I saw this was to redo the stuff that we did in part 1 with constants a, b, and c. I bet it's got a similar formula, but with 1/2 instead of 2. So for me to do Un, I would do something like go back up here. I bet it's an plus b times 1/2 to the n plus c for some different constants a, b, and c. So, just go and do that. Someone in chat has noticed that it's Un is exactly something divided by 2 to the n. There's an n over 2 to the n in there. There is an n minus 1 over 2 to the n minus 1, which you can put everything in Un over a common denominator, and then it becomes that more familiar sum. So perhaps it's just something we've seen before, but divided by 2 to the n, which takes some of the fun away. I think it's actually true that if you replace 2 with 1/2, you can do the same sum again. All those calculations, working out f1, f2, f3, and find the 3 constants. I've done that. That's what I thought we were supposed to do, but turns out it's just a previous thing divided by 2 to the n. How about? The last part of this question is absolutely crazy. If you've had a go at this before the live stream, then I just want to say well done for trying. The sum of the terms sk from k is 1 to n means summing things that were already sums. So this is a sum of sums in a way, except you now have a formula for sk, so you're probably not thinking about sk as a sum anymore. You're probably now thinking about it in terms of that neat function an plus b times 2 to the n plus c, and that's something you could put into a sum. Adding up all those c's is going to be easy. There's some powers of 2, but it feels like a geometric sequence. Things are going to be okay. C squared is a squared b squared is picked up on the trick of asking the same question again, because I didn't do a great job of explaining it before. They're asking for more resources for questions like the Math and Tamua. Last time I said UKMT, this time they've said preferably not just the UKMT, so now I've got to think a little bit harder, right? So what I've normally recommended before are things, there's a list of these on the MAT website, by the way, but let's do a list here. The list normally goes AEA, step support, program, that's pretty good. You might like things on the Enrich website. You might like things on other people's admissions tests like TMUA, or even the physics admissions test. It's a little bit of a rogue pick, but if you like physics as well, then you might like those as well. Other things are available. There are also many MAT past papers. You don't need me to tell you that the MAT exists, because MAT Livestream. And after the summer break, what we're going to be doing is looking at MAT past papers. There's no special worksheet. You're just encouraged to have a look at the MAT past papers on the MAT website, which you can get to from MAT Live. I guess I'll copy them over to the MAT Livestream page just to make it slightly easier, but we're just going to use the past papers off the MAT page. The way they're going to work after the summer break is that we will talk about some of the past papers, like a kind of office hours kind of session. We won't talk about every question, but we will talk about any interesting questions that you want to talk about from those particular past papers on each one. The equation, the equation for Sn has an n2 to the n in it, so this is also a sum that's a bit like an Sn sum. Oh yeah, ENGAA has maths questions as well, so it's all fine. And if you make an open application, just to come back around to the open application question, if you make an open application, the college will not know. You'll be treated exactly as if you made an application direct to that college. They won't know, and they also, in some sense, won't care, because if you're going to... colleges just want good students. They don't mind how they ended up with them, really. Good. Right. Okay. Yep. More recommendations are appearing in chat for things like Isaac Physics, because I've mentioned physics. So if you're interested in that sort of thing as well. I'm going to leave it to you though. We've got a bit of a break. There are, oh gosh, is it 4 weeks? Something like that. Where we're not doing a live stream over the summer. That gives you some time to have a good summer, and I hope you do have a good summer. But also maybe try some of the things on the screen, perhaps math past papers. If you do get a chance to try some math papers, then you might get ahead of me, because I'm going to start from 2007 on the 29th of August 2024. Goodness me. So I'm going to see you after the break. Yeah, this go live thing is going to say we're back 29th of August, I think. Yeah, I have got the date right. It's going to say that we're back 29th of August. Everyone have a good summer. Keep doing maths, and I'll see you 29th of August. Take care. Bye.